everyone. Thanks for joining our talk, High Performance Service Mesh with Proxyless gRPC. So in this talk, we will provide a brief overview of Service Mesh, its evolution, and how Proxyless gRPC can empower you to build high-performance system. My name is Gina. This is Arvind, and both of us are gRPC maintainers and software engineers at Google. And we have been actively involved in leading both the design and the implementation of this implementation, especially around the Proxyless gRPC. So before we start, I'll take a moment to give a brief overview of Service Mesh. The interesting thing is, if you talk to 5 engineers and get them to talk about what a Service Mesh is, you'll probably get 5 different ideas about them. But for today, let's stick with this. A collection of horizontally scaled microservices whose nodes are connected by network infrastructure that manages the connectivity between them. So the first keyword that we have here is microservices, which represent a distinct approach compared to the traditional software systems, where all the functionality is written in one single code base, one single language, and compile into one single binary and deploy as a big unit. One of the biggest disadvantages of this traditional approach is that any bad changes in that release can cause a rollback or delay of the feature that I've been working on for several months. And the microservice is a concept to break it down to the smaller pieces of the service and having them owned by different teams, and they all communicate with each other via gRPC or REST APIs. Here is a simple diagram of a web-based shopping app. So you got a cart microservice, which is blue in the diagram, and you have account microservice in green, and they are both running on 2 different regions. So how does the client know where to send a request for the account service? There are 4 instances of the account services in this diagram. And which one should get the request? And you might also want the client to split its traffic in a certain distribution, or even stop sending the request to a bad backend, a popular backend when they are done. So here comes the idea of network management policies. Developers began to write network policy library, wrapping up all the network API calls to enforce these policies, and it runs with the client application. This works well if you only need to build a library for one language, but in reality, it's not uncommon to see one microservice written in a language, and another one was built with different languages. So you may end up with maintaining a library like this for several languages. And making sure the behavior is consistent across all of them is never been an easy work. So for this reason, Sidecar Proxy were introduced to be run in a separate process with your client application. And Arvind will show more details in the next slide.
Thank you, Gina. So the rise of microservices created an explosion of service-to-service communication, making network management incredibly complex. Let's rewind to the early days of service mesh movement. In early 2016, Linkerd was there at the forefront as one of the first data plane proxies to tackle the challenges of microservices communication heads-on. In its initial version, Linkerd was built as a Pinnacle library, then packaged and deployed within a container. In Kubernetes, this would mean a daemon set. Applications had to opt in to use the proxy. This was built on a JVM, and you would need to know how much the node needs to grow, so sizing was an issue. Envoy came in 6 months later, even though it was used in production and lived since 2015, and implemented a proxy that was more close to the application container. In Kubernetes, this would be another container deployed in the same pod. Istio also built the service mesh by implementing their XDS control plane and using Envoy as sidecars. The proxy was single tenant, which means a proxy is only used by a container in the same pod, which made sidecars a part of application lifecycle. The proxy was tightly coupled to its pod lifecycle, pod termination meant proxy termination, and pod creation triggered a corresponding proxy instance. The single-tenant architecture offered a distinct advantage: streamlined workload identity assignment and granular control over application configuration. After Kubernetes included support for sidecars, scheduling and scaling was easy. But before Kubernetes included the option for sidecars, which are called init containers, it was difficult to manage race conditions in the container. So that means the application had to be aware about the sidecar injections. You need to use sidecar injectors, change YAML files. Another pain point is maintenance. Upgrading the proxy, let's say in the case of like a security vulnerability, wasn't easy. Proxies are lightweight, but you could always end up over-provisioning. So sidecars got us to where we are right now. When service mesh emerged, there weren't as many viable options for achieving the same level of control and observability without sidecars. Then the folks at STO came along and introduced the world to Ambient service mesh. Ambient mesh uses a shared agent running on each node in the Kubernetes cluster. This agent is a zero trust tunnel or a Z tunnel, and its primary responsibility is to securely connect and authenticate elements within the mesh. The networking stack on the node redirects all the traffic of participating workloads through this local Z tunnel agent. This fully separates the concerns of STO data plane from those of the application, ultimately allowing operators to enable, disable, scale, and upgrade the data plane without disturbing the application. The Z tunnel can only perform L4 processing on workload traffic. This is a double-edged sword. It is significantly leaner than sidecars by the large reduction in complexity and associated resources cost, making it amenable to deliver as shared infrastructure. Envoy-based Waypoint proxies are used to handle L7 processing for workloads in that namespace. The networking stack on the node redirects all traffic of participating workloads through the local Z tunnel agent. This fully separates the concerns of STO data plane from those of the application. The Z tunnel, like I mentioned before, again, is required for L7 load balancing, and this becomes an additional hop. So this brings us to Proxyless service mesh, which combines the transparency and low overhead of ambient mesh with the advanced layer 7 capabilities of traditional service meshes. It achieves this by leveraging language-specific libraries or frameworks to embed service mesh functionality directly into application, eliminating the need for sidecar proxies. Moving from sidecar proxies to gRPC proxyless service mesh comes with many benefits. Reduce the complexity of deploying the sidecar and managing its lifecycle. It gains better performance by saving the cost of running a proxy, also remove potential bottlenecks. It provides end-to-end security, close the gap of the last mile security concerns between the proxy and the application. Besides that, you also get to enjoy all the benefits of gRPC functionality, which Gina would be covering in the next slides. Last but not least, gRPC had the foresight to use open standard API, which is XDS, to talk to the control plane. As a client library, it is compatible to any control plane speaking XDS. Over to you, Gina.
Thank you, Arvind. So as Arvind mentioned, Proxyless gRPC service mesh comes with a lot of benefits, and gRPC is providing a number of significant features of the service mesh. gRPC natively supports XDS APIs, allowing gRPC clients to dynamically discover and connect to a pool of backend servers. The combination of gRPC and XDS enabled building flexible and dynamic mechanisms for distributing traffic across multiple backend servers. gRPC has strong security support. You can certainly manage your assets between the workloads by using the client authorization and MTLS in GKE. gRPC provides capabilities to improve the reliability, availability, and efficiency of your microservices. Circuit breaking can be used to control the maximum number of the simultaneous RPCs, and it helps prevent the excessive load. Timeouts allows you to configure the time limits for all RPCs within the mesh. Fault injection provides a way to test your microservices in the presence of different types of failures. gRPC has a bunch of built-in load balancing policies that you can easily configure and start using. And even better, you can do your custom load balancing to bring your own sophisticated load balancing algorithms and plug in to gRPC. And we are excited to announce that we have launched OpenTelemetry metrics recently. And you can find our user guides and more example code at gRPC.io. Retry can efficiently improve your service availability, and it can be helpful if the instances or endpoints are slow or flaky. Outlier detection is another feature to improve the network resilience. The client tracks the success rates of the request made to each backend, and when the backends have unusually low success rates over a period of time, the client will temporarily stop sending requests to that backend. So here we are showing the benchmark results of Proxyless gRPC versus the Sidecar Proxy. Proxyless gRPC delivers a higher QPS, translating to cost saving throughout the reduced infrastructure requirements. Proxyless gRPC also gives you a lower memory usage and the improved application responsiveness. So now let me hand it over to Arvind to show you how you can get started by using Proxyless gRPC.
Now let's define the different planes of service mesh. We have the management plane, the control plane, and the data plane. Let's define them individually. The data plane is the critical path of user-facing functionality, and therefore have to have higher availability requirements than management planes, are more performance sensitive than management planes, and require higher throughput. The control plane provides policy and configuration for all data planes in the mesh. They do not touch the packets or requests in the system, and the control plane turns all the data planes into a distributed system. And finally, the management plane, which is the slow path and configures the control plane. Declarative clients such as Kubernetes operate on the management plane exclusively. Here's a popular example of how the different planes would translate for a mesh setup using Istio. So you can see that the Istio-D is the control plane here, and you're using Kubernetes as the management plane, and you can have multiple variety of data plane implementations being used here. You could also use KRMs to declaratively define your infrastructure. The management plane would push configuration to the control plane, which is Istio-D, and you have multiple options to configure the data plane of your application. Something I would like to draw your attention to is that gRPC can work in heterogeneous environments, so it can coexist with other proxied application or sidecarless applications, which is Ambient mesh. Now, here's another example which you would set up in a Google Cloud Platform universe. You could use gateway APIs to configure GKE management plane or use gcloud commands. And the management plane would then push the configuration to traffic director, which is the XDS managed control plane provided by Google Cloud Platform. I briefly mentioned about gateway APIs in the previous slide. This is an interesting and a very hot topic in the service mesh world these days. Gateway API is an official Kubernetes project focused on L4 and L7 routing in Kubernetes. Initially set out for traffic from clients outside the cluster to services within the cluster, which is basically ingress or north-south traffic. A Gamma initiative was started as a dedicated work stream within the Gateway API subproject, which aims at reusing the Gateway API resources for service mesh use case. So you would make minimal changes to your Gateway API resources and could be applied for service mesh as well. The gRPC API was introduced by Richard Belville from the gRPC team in 2022. The API proposal highlighted the need for a dedicated API for routing gRPC traffic to your backend. There exists an HTTP route, but this could be used to route gRPC traffic, but the addition of new route type significantly improves the user experience. As you can see on the right side, the proposal introduces support for method matches, allowing users to match on gRPC-specific constructs such as gRPC service and methods. This API has graduated to V1 and is released in the standard channel since V1.1, which was a few months ago. These implementations have support for gRPC already, and our team worked very closely with the GCP Cloud Service Mesh team, which was mentioned in the keynote as well, to get Gamma plus gRPC support ready. Google Cloud recently launched Google Service Mesh for preview, so please be sure to check it out. Which brings me to our last slide. Along with the CSM initiative, Google Cloud also proudly introduced gRPC open telemetry support for metrics like call volume, latency, and message sizes. For applications deployed on Cloud Service Mesh, we also show topological mesh information such as the mesh ID, the cluster name, and the service name. So we also have a code lab that's happening right now, but please subscribe to our blog because we have more code labs coming out in the near future. So yes, thank you. Questions?
Hi, has there been any consideration for how rate limiting might be implemented?
So that's actually a feature of gRPC itself. So everything that's involved in gRPC would.
Okay, I may be thinking more like a global rate limiting.
Okay, Richard.
Or you can.
So yes, this is actively in development. There is an additional protocol being created called RLQS, Rate Limit Query Service. There's integration with the service mesh so that from the XDS control plane, we can push down some configuration that says, and please also rate limit based on this additional control plane API for RLQS. The initial support that's coming is Java, and that's slated to come in within the next few months. So you can be on the lookout for that. But if there are additional languages that you're looking for support for, please, create some threads, ask for it, because we prioritize these service mesh features based on what people are asking for. That goes for not just rate limiting, but any other service mesh features that you might have in mind.
All right, thank you.
And I think we'll wrap up the presentation here. And if you have more questions, feel free to find me or Arvind in the hall, and we are more than happy to chat more with all of you.
Yep.
Thank you for joining.
We also have the Birds of a Feather session, so you can join us there. Thank you.